This scattering of data points highlights the core problem of classification. The data exists on two extreme vertical planes, representing a binary yes or no outcome, where a rigid linear axis cannot intersect the discrete values. We solve this using logistic regression. Statistically, it functions as a generalized linear model that estimates the conditional probability of a binary outcome based on input features. While the roots of the method extend into early biology, binary logistic regression was formally established in 1958 by statistician David Cox. The naming of the algorithm reflects its underlying mechanic. It regresses the log odds of a target outcome onto its predictors. The model produces a continuous probability between 0 and 1. Classification only happens in a secondary, distinct step when we apply a decision threshold to that probability. To understand how this works in a production environment, we must derive the logit link, examine why standard optimization fails, and select the right evaluation metrics. These first principles provide the mathematical proof required in sectors like banking and healthcare, where every prediction must be statistically defensible. Applying a standard linear regression to binary data results in a clear failure. The model routinely predicts impossible values, probabilities that fall below 0 or exceed 1. To fix this, we map probability into odds, the ratio of an event occurring versus it not occurring. While the upper limit is now infinity, odds are bounded by a hard stop at 0, preventing a true linear fit. We resolve this by taking the natural logarithm. This logit link breaks the floor at 0, allowing the y-axis to stretch to negative infinity. This creates a fully unconstrained vertical space, where the log odds equal the linear equation, x beta. To return to a usable result, we rearrange the equation to solve for the probability, p. This yields the sigmoid function, which maps our linear predictors back into a range between 0 and 1. This sigmoid curve is the mathematical inverse of the log odds transformation. Defining the curve is only the first half of the problem. We also need a framework to find the optimal parameters for the data. This 3D surface shows the failure of ordinary least squares when applied to binary data. It creates a multimodal terrain where a gradient descent point gets trapped in a local minimum. Binary data violates core OLS assumptions, requiring a shift to maximum likelihood estimation. Maximum likelihood estimation seeks parameter values that maximize the probability of observing our specific training data. By taking the negative log likelihood of the Bernoulli distribution, we generate the cross-entropy loss function. This results in a smooth parabolic bowl. The Hessian matrix of this function is positive semi-definite, ensuring the search space remains strictly convex. The cross-entropy loss function replaces a non-convex surface with a parabolic space that mathematically guarantees a unique global minimum. To find that minimum, we must compute the gradient of the loss function. The initial derivative of the cross-entropy equation is dense, containing complex logarithmic terms. However, the unique properties of the sigmoid derivative cause these terms to mathematically cancel out. This simplifies the gradient to the dot product of our features and prediction errors. Although the gradient is elegant, there is no closed-form solution. We must use iterative algorithms to step toward the bottom of the bowl. While basic gradient descent uses only the slope, industry-standard methods like Newton-Raphson or LBFGS also utilize the curvature of the Hessian matrix. Utilizing this curvature data drastically reduces the time required for the model to reach convergence. In high-dimensional spaces, coefficients can grow excessively large and overfit the noise in our data. We control this growth through regularization. We can visualize the cross-entropy loss as a set of concentric contour lines expanding from the optimal center point. L2 regularization, or ridge, adds a penalty based on the squared sum of the coefficients. Geometrically, this creates a circular constraint. The solution is the point where our loss contours first touch the edge of this circle. Because the circle is smooth, L2 distributes weight across correlated features, resulting in stable parameter shrinkage. L1 regularization, or lasso, uses the absolute values of coefficients, which morphs the constraint region into a sharp diamond. The sharp corners physically force the intersection to occur on the axes, driving specific feature coefficients to exactly 0. This geometric intersection determines whether a model achieves sparse feature selection or smooth parameter stability. Once the model is optimized, it must be evaluated against the realities of real-world imbalanced data. Consider a fraud detection dataset with 10,000 entries. If the fraud rate is only 1%, only 100 dots in this grid are red. A model that predicts no fraud for every entry achieves 99% accuracy while catching 0 actual cases. Standard ROC curves often provide misleadingly optimistic scores in these scenarios because the massive volume of true negatives masks the model's inability to identify the minority class. The precision recall curve provides a more honest assessment. By ignoring the true negatives, it focuses exclusively on the model's ability to identify and isolate the rare positives we actually care about. In production, we rarely use the default 0.5 threshold. Instead, we tune the cutoff to balance the asymmetric costs of missing a fraud case versus incorrectly flagging a legitimate transaction. Logistic regression remains a cornerstone of professional data science because its calibrated output and geometric stability provide a transparent and defensible architecture.